I know that most of you came from my video about Dream, and thanks so much for the overwhelming support, but this video will be a continuation of the series I've started before that, so if you haven't watched it, please do, but here is a quick recap. Throughout the series, we will be looking at the average distance between any 2 points in a unit disk. Even though I already said that it is 128 over 45 pi, we of course want to know how we came up with the answer. By defining the terms probability density and average of a function more precisely, we find that the question is basically evaluating either of these two quadruple integrals. Don't worry, we are not going to do that directly, and in this video we are going to do a numerical simulation instead. We randomly sample a pair of points, then calculate the distance between them. Repeat this say 1,000 times, and then we take the average of these distances. But now there are two questions. First, how do we sample the points? And once we have sampled them, how do we calculate the distance? Let's focus on the first one for now. Since there is circular symmetry involved, it's natural to introduce polar coordinates to our picture. So to specify a point, we need to generate two pieces of information. R, the distance from the origin ranging from 0 to 1, and theta, the polar angle, ranging from 0 to 2 pi radians. So to sample a point, we simply select the value of r from 0 to 1 at random and theta from 0 to 2 pi at random. Let's say we have chosen the values r1 and theta1 respectively, and repeat this to choose a second point. Then from the law of cosines, we can calculate the distance using the formula. So we are ready to perform a numerical simulation. There's a spreadsheet in the description for this, and we get this average from the numerical simulation. The exact answer should be 128 over 45 pi, which is around 0.9054, but that's quite far away from the answer we obtained. It is theoretically possible that we just happen to pick pairs of points close together, but we need to have incredible luck to lower the average that much. We are going to calculate this luck later on in the video, but anyway, that means either this exact answer is wrong, or we have done something wrong in our simulation. It is very clear which one it is when we plot the points that we just randomly picked. The points are more concentrated near the origin than towards the rim of the circle, and so the simulation has gone wrong somewhere. The reason is that when we randomly generate a number for r, half of the time it returns something less than 1/2. However, for the disk, the inner half only occupies an area of pi over 4, and the area of the whole disk is pi, and so the ratio is a quarter, or equivalently, we should only have a quarter chance of picking r to be less than 1/2. But how do we address this discrepancy? Let's denote x as the value of r if we simulate it correctly, and y as the value of r generated by the computer. As discussed before, the probability that x is less than 1/2 is a quarter, and that y is less than 1/2 is 1/2. More generally, the probability that x is less than r is the area of this inner disk pi r squared divided by that of the whole disk pi, so the probability of x less than r is r squared. And if we again consider the same probability but for y, it will be the proportion of the smaller interval, which is simply r. Here, r can be anything really, so as long as we put the same numbers here, this equality still holds. We want this probability to be r squared because it will then match the probability for x. To do that, we can simply change this r to be r squared so that we have the same numbers in the two boxes. So now we have this equality. However, saying that y is less than r squared is the same as saying square root of y is less than r because everything here is non-negative. Comparing these two statements, since they are true for all values of r, x and square root of y have exactly the same distribution. Intuitively speaking, if I have two computers generating x and square root of y respectively, nothing can tell the difference. X is what we want, while square root of y is what we can do. But since there isn't any difference, we can use square root of y to model x. In other words, we use the normal computer-generated value, then square root it. So in the numerical simulation for R1 and R2, we generate a random number, then square root it. What about θ1 and θ2? Do we need to do anything to it? No. If we similarly denote x to be the correctly simulated value of theta and y the value of theta just from random number generators, the probability of x less than theta is the proportion of the area of the sector, which is theta over 2 pi. And for y, the probability is the proportion of the length of the interval, which is also theta over 2 pi. So x and y are already the same in distribution. That means we need the square root adjustment for r's and nothing for thetas. If we really run this approximation is much closer to the exact answer. More generally, if the probability that x is less than little x is some function f of x, we can similarly consider the probability that y is less than f of x, which is again f of x. This time we apply the inverse of f on both sides, so we have f inverse of y smaller than r. Again, comparing these two statements, x and f inverse of y are the same in distribution. In the previous example, f of x is x squared, so f inverse is simply the square root. In practice, we sample y from a built-in random number generator, then transform it using f inverse, which is why this technique is known as inverse transform sampling. The good thing is that x can be anything you want, so you can simulate any distribution. But this technique is only useful if f inverse is easy to calculate. For example, if you want to simulate the normal distribution, f is already pretty complicated, let alone f inverse. In those cases, it's better to use other methods like the Box-Muller transform, which isn't the focus of the video. That's all well and good, but let's say we don't really know this exact value. Of course, the numerical answer should be close to the exact answer, but how close? What I'm about to say is the big picture, otherwise the video will be unbearably long. There will be links in the description for more of these details. In the numerical simulation, we have this distribution of the distances. In particular, we want to find the standard deviation, a sort of average deviation from the average, or mean in statistical terms. If the standard deviation we calculated is Sn, then our estimate of the actual standard deviation is S, which is Sn, but adding a correction factor in front. It is possible to have picked points very close or far away from each other, but these extremes should cancel out when we consider the average, so the average should behave nicely. Indeed, by the central limit theorem, if the actual mean is mu and actual standard deviation is sigma, then the average of the samples taken should approach normal distribution with mean mu and standard deviation sigma over square root n, where n is the number of samples taken. So graphically, this is how the sample mean should be distributed, with mean mu and standard deviation sigma over square root n. Equivalently, if we consider sample mean minus mu, we only shift everything by mu, and so the peak moves to 0, but everything else stays unchanged. It is entirely reasonable that the difference between the sample mean and mu ends up here, but it's extremely unlikely for them to be that far apart. So we can be reasonably sure that the difference is somewhere here. More precisely, the probability that the difference is here is the area of the region. So if the area is 0.99, then we are 99% sure the difference ends up somewhere here. So this interval is known as 99% confidence interval. All this is to say that not only can we approximate the average, we can also in a way approximate the maximum error. But there is a caveat. In the central limit theorem, we need to have the actual standard deviation, but we can only estimate with this correction factor. So to be more accurate, we should use the t-distribution with n-1 degrees of freedom, but if n is very large, there isn't any difference with using normal distribution anyway. Now, in the first half of the video, I said we would calculate the so-called luck that we get the average that low if there is nothing wrong with our simulation nor the exact answer. The above discussion works here as well, but this time the difference is really large. we can calculate the probability that it is at least that extreme, and it turns out to be in the order of 10 to the minus 39, or if you want, 1 in the 141 undecillion, 141 followed by 36 zeros, which is so low that it is much more reasonable to conclude that one of these is wrong. What I've just described briefly is called a single sample t-test, and as said before, there are links in the description if you want to learn more. The next video will be a concept called the Jacobian. This will be the prerequisite for the final video finally explaining how to solve this problem exactly. However, I'm sorry that it will take a long time for the next upload, but hopefully it should be worth the wait. If you enjoyed this video, please click the like button, subscribe with notifications on, as well as commenting on it. See you next time!